G'day guys, we've got an interesting geometry question today. I don't know where it's come from, but apparently it's from an MIT entrance exam from the year 1869. So, things have come a long way since then. I'd expect a advanced 14-year-old could be able to do this question. So let's have a go at it and see what happens. So, the perpendicular is dropped from a vertex of a right angle upon the hypotenuse, divides it into two segments of 9 and 16 feet respectively. Find the length of the perpendicular, that's middle side, and the two legs of the triangle. Alright, so let's draw in what we've been given. We've been given that this is 9. We've been given that this is 16. Cool. So we have to find this side, one of the legs, A. You need to find this leg, B, and we need to find the perpendicular. We'll call that C. Now, there's a lot of different ways you can do these sort of problems. Like you can do them using similar triangles. I'm going to try and do something a little bit different. I'm going to use Pythagoras and a few sort of equations, and we're going to, substitute. This is just how naturally I would solve this problem if I hadn't seen it before. So let's go about finding some equations. So the first obvious Pythagorean, relationship we can have in this triangle is the big triangle, and so we can say that a squared plus b squared is equal to 9 plus 16, 25 squared. Great. Now the next thing that's a good starting place. Now, what we can do is we know that b squared is not only just this the bottom part of the big triangle, one of the legs of the large triangle, it's also the hypotenuse of this smaller triangle that's in here. So what we can do is we can say that, well, c squared is equal to b squared take 16 squared. Now that is just a rearrangement of the Pythagorean triple. We can also set up an equation using this c here, because this c here is not only just this side of this pseudo-large triangle, it's also the bottom of another triangle here, the smallest triangle of our set. So we could say in this case that c squared is equal to, now the hypotenuse is a, so a squared, subtract 9 squared. Cool. So from this, hopefully you guys are sort of cluing on to what I'm going to try and do here. I'm going to use these two equations and the fact that they both equal c squared to make them just equal to each other. So it gets rid of that c squared term. So I'm going to say that b squared minus 16 squared is equal to a squared minus 9 squared. And now we've just gotten rid of one of our variables. So that's a good start. So what we can do now is we can make all of this in terms of just b squared. We could say that b squared, we could plus 16 squared to both sides, is equal to a squared plus 16 squared minus 9 squared. Cool. And from that, we know that we've got 16 squared, which is going to be 2 to the power of 8, so that's 256. So we can have b squared is equal to a squared plus 256 minus 81. So once we do that, we can go, well, 256 minus 81 is going to be 175. So we could say that b squared is equal to a squared plus 175. Cool. So I'm not really using a calculator here, so that's why it's taking me a little bit longer. I'm having to do a few extra steps. But if you had a calculator in this, I don't know if they had calculators back in the 19th century, so we're trying to maybe do it the same as they did it back in the day. So we don't want to give ourselves any undue advantages. So what we could then do is, with this formula that we've been given, I should be able to, well, not should, I will be able to substitute that in for b squared in our initial equation, which is pretty clever, to be perfectly honest. So let's go about doing that. We're going to have a squared plus, now instead of writing b squared, I'm going to write what we figured out it equals. A squared plus 175 equals 25 squared. Cool. Now we can simplify this. We can say 2a squared. Now I'm going to move the 175 over to the other side, and I'm also going to actually compute this. Now 25 squared is 625. (625) minus 175 is 450. A squared, would that make it be 225? Yep. And then once we've got that, we can then take the square root of both sides, and we can write that a is equal to, now in submaths, if we took the square root of this, we'd have to say a is equal to plus or minus 15, but minus 15 doesn't really make sense in this sort of case, so we can just say a is equal to 15. So let's substitute that in. Cool. So I would then go about working out what we have for C. There is no real correct way. Once we've figured out one of the extra sides, the rest is going to fall down pretty easy. So let's go for C squared now. Now we know that C squared is going to be equal to A squared, or 15 squared, subtract 9 squared, which is equal to 225 subtract 81. Now, 5 take 1 is 4. We got that it's equal to 144. So we know that C is going to be equal to the square root of 144, or 12. Cool. And finally, we're looking for b squared. So we could say that b squared is going to be equal to 12 squared plus 16 squared, which is equal to 12 squared is 144 plus 256. Now, we add those two together, we get 400. And so we can say that b is the square root of 400, or 20. Cool. So what I've done here is the important part which allowed me to solve this problem is figuring out that we could have two Pythagorean triples equaling the same number. And if we do that, we can make them equal to each other, and that gets rid of one of the variables. So that will allow us to calculate what each of the numbers are. But until you do that, it's going to be quite a tricky way of doing it. You're going to have to use similar triangles, and to be perfectly honest, some people like that method. I don't personally. It's just personal preference. But the only problem with the doing it using Pythagoras, especially if you're doing it in 1869, is that you wouldn't have a calculator. So you have to be pretty sharp with your mental maths, and or you're going to have to spend a lot of time in the margins of the question figuring out what 16 squared take 9 squared is. So what I would recommend is that you go through all of your square numbers. Know that 2 squared is 4, 8 squared is 64, 12 squared is 144, 13 squared is 169. As if you get all of those up to about 20 squared, you should be okay. So, this was an entrance question for MIT in 1869. We have progressed a lot. I can't imagine this would be a current MIT entrance sort of question. However, I think where students today would struggle in this, again, is we're doing the mental maths. We are conditioned from such a young age to use calculators when the numbers get a little bit big. And I think, and I tell a lot of the kids that I tutor, that it's important that you actively try and resist going to a calculator until it's absolutely necessary. So I hope, this video was enlightening, and if you did like it, give it a thumbs up, subscribe to my channel, and I'll see you guys back here next time.